Hi, I'm Kellen Yu, and I'm representing Stuyvesant High School, which is located in New York City. With this year's theme of climate change in mind, I decided to focus on water. The transportation and processing of fresh water has a very large carbon footprint, with experts estimating that for every cubic meter of water consumed, 10.6 kilograms of carbon dioxide is generated. Due to the fact that agriculture accounts for about 70% of the world's freshwater usage, I decided to focus on reducing water consumption there. Farmers typically indiscriminately water their crops. The problem here is that water is not consumed uniformly throughout a plot of land. Some spots of land have too little water, and some have too much. If we instead use a selective approach to watering, we could save water and also prevent overwatering, which can introduce diseases to the plants. One of the biggest challenges in this selective approach is knowing the moisture levels of each area of land. Sensor systems already exist for this, but they are very expensive. This is where my project comes into play. I created a very low-cost water moisture sensor that is very simple to set up and use. The working principle of this sensor is that a capacitor with the soil as its dielectric will have its capacitance change according to the moisture levels in the soil. By using a simple RC circuit, I can measure the rise time and fall time of this capacitor in order to find the capacitance, which then leads me to find the soil moisture level. Everything here is integrated onto a single PCB, with a capacitor for measuring the moisture drawn out as large traces on the PCB. The components are protected by a simple 3D printing housing, which uses no screws whatsoever. I built my project around the ATtiny414, which is a cheap and effective Arduino-compatible microcontroller. One of the main contributors to the high cost of conventional sensors is that they require expensive low-power radio transmitters and corresponding receiver towers. I decided to ditch radio and instead communicate the soil moisture by using LEDs. At night, either a drone or any other vehicle can travel to these sensors and using computer vision find out which color LEDs are activated. Just a red LED corresponds to the soil being too dry, green corresponds to optimal range, and both red and green correspond to the soil being too wet. In order to save power, a phototransistor is connected to the microcontroller. Usually the device is in a power down mode, but when light gathered from a drone or the sun shines on it, it will trigger an interrupt service routine, causing the microcontroller to wake up, measure the soil moisture, light on the corresponding LEDs for a few seconds, then go back to sleep. The interrupt will only trigger on the rising edge of a signal, so when the sun is up during the day, the microcontroller will still be able to sleep. Here in the demo, you can see a few sensors placed in my front yard. A drone follows GPS waypoints to go above the sensors, and its camera feed is processed to read data from the sensors. One challenge that I faced was trying to get interrupts to work. It was my first time using ISRs on such a low level, and even when I did manage to format things correctly, the microcontroller just wouldn't wake up reliably. I eventually found out that I had what was called a floating pin on the photodiode pin, and had to place down a last-minute pull-down resistor, which fixed the problem.
Thank you for watching my video.